name is Pablo.
So then let's begin instantly. I don't know who was here last year. We were 3 of us and presented the LibreSilicon technology. And now there's a short update on it. First, disclaimer, because this is somehow, And now a short overview, what I want to show you. I will present you the current state of the LibreSilicon project, then start at the basics and standard cells, and continue the fourth one. So the update first. The Leviathan had a lightning talk in 2017, and he said we need some free technology. I found, I really liked that idea, and we met, and in 2018 we began to think about this idea, and also began with on a 1 micron technology. The reason for 1 μ was because it's quite fault tolerant, and it's the most, it's quite maker-friendly. It's and it's still documented. This was current state of the art in the late 70s, beginning of the 80s. You still find books about it, and that's about the 486 generation of technology, chip technology. So last year we presented our test wafer, and since then, so basically this year, we we didn't have any money anymore to rent the clean room. We had the riots at Hong Kong, which led to the university being closed. They said we just we finished the semester earlier, so we don't have a clean room anymore, and had to focus on paperwork. It's not that ideal, so we are looking for alternatives. So if anybody of you has access to a clean room, please let us know. Because of the funding thing, we have also a GoFunding campaign running. So it's not a topic for everyone, I admit. Some links. First, LibreSilicon, that's the project page, our homepage. Then we have a GitHub. Our standard cells are published on GitHub. That's our main repository. And then we also have a wiki where everything is documented, also the things that I present today, because I saw that there isn't that much documentation in this field. It's missing in the mass among the makers. So if anyone wants to start play around with it, that's what you need to enter in your terminal, git clone, and then clone the standard cell repository. And the design flow for chip design is usually, you begin writing your code in Verilog, VHDL, Spinach, HDL, whatever. Then you simulate it. There are also free tools. And then you try to synthesize it. And it's a kind of compiling. We have the Yosis tool, which can do this. It understands ASICs, but also FPGAs. After compiling it or synthesizing it, you get something called netlist. That's called like this because it contains a bunch of gauge, of latches, flip-flops, cells, etc., and the connections between them. These cells need to be placed somehow on the silicon. they are placed within the layout. So we need some layout information, which layer they use, how they are built, and in the end you get a GDS2 file. That's something similar to the Gerber files in PCB design. These files are used for the mask production. And now we are talking about these standard cells. The design goals, or the goals of such a library, if we have a look around at GitHub or somewhere else, we usually find student projects which have shown, yeah, we can do some cells, but it's quite limited because, yeah, typical student library, it has 30 to 40 cells, but this is not enough for a real big design. There are cells which simple cells, things like AND or XORs, flip-flops, latches, but that basically is it. But the complexity can increase a lot. So commercial libraries have between 150 and 200 cells. So, for instance, they contain more logic to test them. So, yeah, that's something I would like to solve another way, but it doesn't matter now. Our goal at LibreSilicon is we want to have need at as less as not too much energy. So we began our design in an ideal way, considering the energy usage, because CMOS technology, it uses energy when switching. It doesn't use current or energy when it is in a static state. It only uses energy when switching.
So it doesn't need any energy just when the change comes and the elements change their state. Then there's a state where the transistors both open and there's both need energy. We also want to have fast cells, as fast as possible. It sounds maybe a little bit contrary to the requirement before, but we can make these things really small and find a good compromise. And we also want that the cells are small, because in the construction you don't pay for the chip what's on it, how many gates or what functionality, but you pay for the area of the chip. So that means if you have a cell library which is small, and you can also make sure that the design is really small, then the chip will be cheaper. Okay, so these are some standard cells. That's a very typical, maybe you know it from the university, it's a NAND with two inputs. Left is the symbol, and on the right there's a table. And if you have a look, for the NAND it's really typical. So as long as both inputs are not 1, the input is 1. Only when both inputs turn on, then it goes to 0. So that's the inverted AND function. On the bottom you can see the formula in the typical notation which is used usually. And that's how it looks. I'm sorry for the graphics I generated, and there are some artifacts inside. But the principle should be clear. You see the transistors, you see the input channels, you see the P channels parallel. This is NOR. This is kind of inverse to the other gate. Rechts the table. So here it's typically when both inputs are 0, then the output is 1. But as soon as one input is 1, the output will be 0. And the notation down below again. And here the transistors. You can look at this as mirrored. On the bottom you have the input which are parallel, and then on the top the P channels which are parallel. This is an XOR, an exclusive OR. So we also have the table here. So both inputs must be different so that the output will be 1. Otherwise it would be... I don't have an implementation for this because there are 5, 6, 7 variants, and which one will be in the standard library I have not decided yet. I will think about this in the later point in time. That's the inverse version of the XOR. It's usually called NEXNOR. I call it... It's an XOR but inverted. So when both inputs are different, then you have the 0. When they are the same, then you have the 1. There's the same amount of implementations in the literature. Now it's getting a little bit more complicated. These are some examples of cells which you can also think about. So these are called complex gates. When you look at the top, so you see a small function on the top, an AND or an OR, and then you can change them, and then down below you have the variant where you have 2 gates at the beginning and then 1 gates at the end. And this principle of concatenating transistors such that this comes out is you can do this as far as you want. And I want to do more of these complex gates in the standard library. So I have to explain something about this. How far can you go with these complex gates? So this is an example for an MENT with 4 entries. I don't know if you remember the end from before. So here down below the transistors, in serial transistors, and at the top you have the parallel. It's an AND, so I overlooked the buffer at the end. So there's like a small inverter at the end. So it inverts it, so I have an AND and not an AND. So let's start explaining this buffer. So there's a design decision I made in the standard library. When we imagine over each transistor in the long channel, the lower end and the one above, when there's like a voltage decrease, so so there could be a small difference, but when you have like this difference 4 times, then this difference adds up, and this can cause that the output level is not really big enough. So it's not really on the level it should be to be used further in the circuit. And this very trill possibility. And that's a problem because you actually want to use this level somewhere else in the thing, and you fix that by adding an inverter, because then you have like clearer different levels. And one design decision I made, so I look at how many transistors are serial. How much do I have to buffer at the end? So I have like maximum 4 transistors here, but that's configurable in the tool. But I can think about places where I do 3 or 2.
So 4 transistors is okay for 1 micron, but with smaller technologies we have a voltage problem. The voltage at the gate will to source, I'm sorry. There's a certain threshold voltage when the transistor effectively is in operation, and this is not yet. We have to limit these voltages and limit the number of transistors, so I added a second parameter which tells up to how many transistors are allowed in one chain. So the first one is when to add the inverter, and the second one is maximum numbers of transistors in one row. So it's called stacked. There's no German translation of it, but yeah. If we stack 2 transistors because of the threshold voltage, then the operating voltage would be too low, and so the library would be too small. So we are at the level of these student libraries, which we want to do bigger libraries. When using 3 stacked transistors, we have libraries. Yeah, but yeah, some libraries don't support it. But if we add 4 stacked transistors, then the library will be hugely complex. So in the paper I read that there are up to 4,000. I will tell more about this later. So we have a buffer limit at bigger or equal to 3 transistors. So how do we get to these complex gates? We had the 4 examples. We start at one complex gate and go to the next by applying small hints. So we can add a transistor to the pull-up or pull-down network in serial. So, but then we have to add in the complementary network a logic equivalent in parallel. That is quite easy in CMOS. So I wrote a tool for it, but it's still a bit buggy. So add in series for one network and in parallel for the other one. If I add a pull up in the one network, I need a pull down in the other network. Because this is a thing which didn't really exist yet, I began with some paperwork. I said, okay, I begin with a most simple CMOS network that I can imagine. That's the one in the left, that's an inverter. This inverter, with this principle, I can add more transistors and then make a NOR 2 out of it. That's a NOR with 2 inputs. So we see the A transistor has gotten a little brother, and B has a second one too. That might look a bit strange, but that's the basic idea. I did the same for an AND. I started with the inverter, and then I said, now I start. I extend the pull down in series and the pull up in parallel, and then I continued with that. So I continued with NAND 2 to NAND 3, etc. And I arrived at a cell which looked like this. some people already thought that I was a bit Meshuggah when I was drawing such things in the club, the makerspace. So these are 4 of the examples which I scanned for this talk. Some of them are not even in the make file, but yeah, I did quite a lot of paperwork, and the current state of this is I have 2 big folders full of papers. Only these derivations, I estimate about 500 to 600 cells, all with this limit of 4 stacked transistors. And I have the impression that I'm far away from being complete, because the cells tend to create big trees, like with this one. We see and, or, etc. We see it in the picture on the right upper corner, how it looks in a more abstract way. Yeah, it was a lot of work. So this is an intermediate thing. It's a bit more filled because we have 2 ORs or 2 AND functions. Okay. And all of this work, which I did on paper first, I wanted to have somehow in my tool. So I said, okay, we need a tool. First I have the thing, this I will present you. If it works, I have to close that one first. So that's the tool, apparently. So. So I'll do a make, so it makes the man pages, and I will have a look at them with you together. Oh no. Why not? Is that a typo? Probably. So in German it's called the Vorführeffekt, presentation effect. It works every time except in the presentation. So, sorry. So that's a GUI version of it. I called the tool popcorn because the cells, it feels like making popcorn, because all these cells are being generated like when putting corn in a pan and making popcorn. So you can have a look at it. It is in the GitHub repo with a short description on how it works. We see as options, we have the buffer limit, cell names. You can add a description for the documentation. There are some formats which are not all of them yet implemented. The number of stacked transitions and methods which can be applied. As I explained, you can add more transistors in series or in parallel. That was a simplification, because based on which cell I'm currently am, I have to adapt the naming to. So should I add the next letter because, yeah, should I just renumerate them or add new letters? And so I have different options how it's done in the tool. There are also more options. Not all of them are implemented already now, but okay. Let's continue here on the presentation. So the principle, as I said, with this tool, I take a cell file, a cell description file, I feed it to the tool, and I get some other cell file, an extended cell file. I'm just looking for such a cell description. So that's how they look like. They have, yeah, that's a description of this cell file format. It can have commands. I can define cells, inputs, outputs, output equivalent, define clocks. And I also have a .end to be sure that the file is complete. And then a big number of transistors. All of them have a name inside the Git. They are. I have a number in it, how many transistor in the stacking this is. So I can let it draw. I can let the tool draw schematics. So there is also information for the X and Y coordinates on the schematic, and size is another thing. I want to write in the size of the transistor. There is a method to do the right dimensioning, to do the right the method is called logical effort, and it optimizes between energy usage and size of the cells. So it's not done on the fly, but when the cell is created, it computes the value needed. But we don't only have complex gates, we also have, for example, latches. These are memory cells. So in German, these cells are also called flip-flops, but I think this is not correct. These are cells which are memory cells, but they are driven by the clock, in Taktzustandsgesteuert in German, and in America it's just called latch. So if we look at a high level or low level, this thing is transparent, and if we at a low input level, it saves the value. In addition to it, there are flip-flops. They are triggered by the rising edge of the clock. In the principle, flip-flop is nothing else than two latches in series. So if I have a low active latch at the first stage, then can do a flip-flop. So the first, at the falling edge, it is transparent, but at the second one is then not transparent, and so it becomes only usable when on the rising edge of the clock. So latches, only when the input is on, and flip-flops are triggered by the rising clock edge. That's the difference. Now back to the slide. On the left we have two inverters. My signal is X, I invert it, so I get a signal which is phase shifted by 180 degrees, and the second one is then phase shifted by another 180 degrees, and what I get is the same signal, but it is buffered, so I have a less big load. So when I have a two-phased clock, I can use this for the later transistors in order to switch them. So if we have a look at this stage up there, that's an inverter. It can be, but it can be three-state. This means when the clock, the lower and higher transistors are in a non-ideal state, then it doesn't matter for me what's in the D input. It doesn't let it through. It doesn't invert. It can drive when the clock is correct, then it drives. But from the right, the feedback, we also we have the feedback loop. So it cannot. The left and the right inverter are both driving the middle one, and the Q is the data output.
That's the smallest latch circuit I know. That's the same for low active D-latches. So with the N, the NOT at the end. I have exactly the same circuit, but the clock signals are the other way around in comparison to the one before. So to make it a little bit more complicated, I have an example where I have a latch which is high active, so with the positive edge, so with the positive latch, which has a clock enable, so I can allow the clock or I can disallow it, and it has an asynchronous reset. And this whole circuit is optimized to have the minimal amount of transistors to have this. So it's the minimal design. So my reset is at the top, called P3. That's high active. If I had a Z active, it would be low active. The clock enables signal I have at the front. It depends if I have a high active or low active clock signal. This point is an open stuff. Too much to do. I want to go from a schematic to my cell file. For the schematic, I used an open source tool, which comes from the PCB area. There is the possibility to write an exporter, a netlister. I will do this for all cells I have to create by hand. So let's quickly do that. So let's have a look into the catalog. So there's already something. So let's remove it. Okay. So we have some makefiles in there. So catalog is a folder where all the cell descriptions are. So I have some with stacked. This tells us the amount of stacked transistors. So the ones with 3 stacked transistors are in the file stack 3. So that's the good thing about this is that so if I know what the limit is, I can use the correct makefile, and then the other ones are included if necessary. So with make catalog you can generate the catalog. So let's try this. Let's try that out. And that's where it actually crashes. The reason is because my cells are not continuous right now. So there's some which it cannot generate right now. So I really have to go through it from the start to the end. So that would be the workflow. So I have all the stuff in the make file, and then make generates me all the combinatorial cells. So the warning is that's serious. So if you try to do this, yourself or to generate it yourself, so you should know what you are doing. So the effect onto your circuits or your layout can be disastrous. So my make files usually have a help screen included. So let's do make. I get a help screen. In this case, it's the global help. So I have the possibility to create a distribution. So make tools I already did, make catalog we also did. I can also generate the documentation for it. So to generate all the diagrams we saw earlier and all the documentation I showed, how the schematic looks like, what files it needed, everything, simulation files, that's all in there.
Okay, jetzt wird es nochmal ein bisschen blutig.
Okay, now it's get a little bit more difficult. So there are Moses design rules. Moses is a program by a US American university. It's comparable to the European Euro practice. They offer a service for universities where you can say, hello, I have a chip, I want to do stuff, and then they create a multi-stuff wafer for you. And then they send you a small amount of these wafers, and that's it. But they also defined design rules. They designed the distances, the dimensions, the metals, everything. And these rules are made such that you can apply these to a lot of different technologies you might have. So it's the smallest common denominator. But the good thing about this is that it's really robust. You maybe not have the bleeding edge stuff, but they should be working usually. So you can work very good with it. And these rules, you can get them as a PDF document. They are well written. So these rules are defined in three steps, like as CMOS, scalable CMOS technologies. So they started with 2-3 microns. Then there were the submicrons. Like, so everything roughly smaller than 0.8 mu. Yet another step deeper, there are the deep submicron technologies. So you have like really strange effects already in there. So the dimension is smaller than 0.35 mu. Today that sounds really, really huge. So I added a fourth step into these rules for me. So, okay, I wanted that people are able to add a custom rule file themselves, so they can do stuff which diverges from the already available rules. So I will show you how this looks like.
So one more typo that was. So a lot of header first. And description. It is written in Scream, so these are the rules that exist. The numbers are the same as defined in the PDF. Define a small vectors where the 4 values are written, described in it. And this is roughly where it begins. It also has ASCII art to explain these rules. For the instance with rule 1.1, this n-well width needs to have a minimum value. And the entire document is done like this. And you always have a short description and then a table depending on which Moses rule you take. And I use these rules for the layout tool. Oops, that was too fast. So these rules are all lambda defined. That's an important point. Lambda means half of the feature size. So if somebody says we have a 1 micron technology, then lambda is 1 micro. Then the size is 1 micro, and lambda is half of it. And all the rules are given based on this value. It doesn't. The rules are not written in 0.8 microns or so. They are written in more or less integers of lambda, and this has the advantage that you can scale it up or down during for different technology generations. That that works surprisingly well. Not for all things, but for most things it works surprisingly well. So now here we have one cell. Another thing that I have to explain, this is a 6-track cell. The brown lines are metal. So we have one ground and one supply voltage. So these things have rules. The tiles are the lambda. So we see in the Moses rules this has a size of 4 lambda. And the Moses rule also define the difference to the next metal. So we have 4. This gives a grid of 8 lambda. And this grid is also used when routing. On amongst different cells. And that's what is called tracks. And usually in this area, the cell size is written down in tracks. So this is a 6-track cell. It has a size of 6 tracks. And there are also bigger cells. This is one with 7 tracks. The grid is getting smaller. We have one with 10 tracks. And so for a NAND 2, 10 tracks is quite big. There's quite a lot of room in the middle which is not used. But for complex gates, it's not that much space. So you always have to find a compromise between wasting space and having enough functionality in one cell. So what can we do with this? thing.
Wo ist es da? Also, wenn ich das jetzt hier mache,
So when I do the following,
Templates,
I
halt ein TOML-File drin
we have a TOML file in this template,
und das ist dazu gedacht,
and
die
it is
Konfiguration zu machen. Also,
used for the configuration.
da sieht man wieder das Limit
I
4. Also, wie viele
write,
Transistoren ich stecke.
we see again this limit of transistors, which shall, yeah, of stacking limit for the transistors, when to add buffers,
Das ist mein Beispielfall, was ich habe.
then add the size in tracks of the cell. Physical. Ja.
Denn Terminals, also auf welchen
Then
Ebene mache ich die Übergabe zum Routing?
there's,
Also das ist für sozusagen
yeah, which layer is responsible for routing? Where should the when is a cell finished and when should the router begin?
Ja, Connectivity, Restricted, es gibt auch solche Sachen, dass man sagt,
There's a thing called connectivity, which tells, for instance, you have to connect it horizontally only or vertically only, or it's unrestricted. I said for my library it's not restricted. We have more things, transistor things. It's the width of the channel, for instance, and the other ratio between the height and the width of the channel. So if I have a feature size of 1 micron, then my lambda is 2 and the width would be 3. So now there's a next thing which is called gamma. I try to explain. The charge carrier mobility is different for p-channel and n-channel MOSFETs. So in one we have the electrons moving, and in the other one we have the holes moving, and this mobility, the speed is different. So, and this should be equalized as much as possible. So you make the p-channel bigger, and the ratio of how much bigger the p-channell is usually defined as gamma. I added a value which works well for many cases, but it depends really on the silicon. It's usually between 2 and 3 somewhere. So if I wanna have something which is resistant to side channel attacks, then it's important to balance the value gamma. Okay. That's yeah, I had to skip some slides, but this is my goal, where I want to be one day, that the TOML file configures itself, so you just can type make dist. It would of course take a while, but you get the right layout, the right documentation. You would have a ready to start library which contains everything. So, and yeah, of course everything is also open source, as you see in GitHub. Thank you, Chipforge, and thank you for listening to the translation. If you have feedback, you can send it to Twitter on the hashtag C3T, or you will reach us on c3lingo.org. We have a question from the internet.
Hallo.
Yeah.
Die Frage aus dem Internet lautet,
So the question from the internet is, how expensive is it to have 1 square millimeter of area on such a die, and how much time would it need?
Okay, our background is we want to create a free silicon, so we also want to make this process free. So that's what our drives us. So this square millimeter there, the wafer cost would be 100 Hong Kong dollars. So it would be about $10 for wafer, 4-inch, pretty small. And there would also be the mask cost. It will be about up to $10,000. The rest is manpower in the laboratory. And you can make as many chips as you like from that. We would like to go back to the laboratory, but we need money for the cleaning.
It looks like you can, or you want to auto-generate the layouts for your standard cells. Can we also do this directly in the tool? Would that be possible? So the tool can synthesize macro cells by itself? I could imagine this for smaller cells.
This way would be quite complicated. Actually, the tool like Yosys, which make the synthesis, depend on how good is the library you're using. But if we have a library which is quite constrained and small, users can only small solutions or not so good solutions. But when we are able to create a library using this popcorn, which is really good and has a lot of stuff, then users has a lot of possibilities to optimize the actual circuit. Speaking about delay, energy consumption and stuff like this. So we give the tool more possibilities to do the layout. It could be that it takes longer because it has to search a bigger library, but the results will be better.
Okay, als nächstes am Mikrofon 1 bitte.
Okay, also das sieht ja schon mal ganz gut aus, aber
I'm really impressed, thank you. But did you also do transmission gates, Schmidt triggers, or analog multiplexers?
Okay, those things I do not generate with podcasts. The multiplexers I do by hand. Multiplexers are in different stack cells. The transmission gates in the multiplexers have a big disadvantage because they go into my count of stack transistors. So if I have these in the path, so I have to do a renewal or refresh of the level if I have these included. So this stuff I do by hand. And the Schmidt triggers should not be in the standard library. They should be somewhere else.
Alles klar. Dann war noch eine Frage am Mikrofon.
Thank you. Microphone 2. My question, you said that you want to open source this process from chemistry, from the chemistry point of view. If you more or less know which chemicals to take, how realistic is it that a hobbyist can do this safely? And are there any plans in these directions to promote this among the makers?
Yeah, that's a good question. You should know what you're doing. There are chemicals involved, so you can burn your clothes with this stuff. So we all tried this. So there are people who do this in their kitchen. For example, like Jerry Ellswood, the one with the C64 hack. So there are videos on YouTube where she has a furnace where she does the stuff in her kitchen, and she plays with steaming sulfur acid, and she does it. Just go to YouTube and take a look.
Yeah, and suddenly you have the police in front of the door. Do we have more questions? Yes, we have. You showed some of your standard cells. How about the timing and the simulation for the entire place and route, etc.?
Yeah, that's true. This point was a little bit short because of the time. So when we have the layout, so then we use this magic layout tool, and then we do a parameter extraction. So we get a spice model out of this model, and with the capacities and the resistances. So I have so I have stuff like when there's 20% of this level or this edge, I have 80% of that edge. So I have like some automatic
Ja, die nächste Frage
fixing
an
of this.
Mikrofon 3.
Ja, danke schön. Habt ihr schon
Did you
Simulationsmodelle von euren
do
Transistoren,
simulation
die ihr dann
models of
Spice
your
nutzen könnt? Weil das
some
ist
transistors that you can use inside SPICE?
recht viel
Because
für viele Technologien, deswegen ja auch
yeah,
die
for many
gleichen Modelle, so
technologies,
Standard aber gibt's schon
these are
gewisse
available. So
Simulationsparametern von den Transistoren, die
Are there
dann gefertigt werden.
other simulation parameters available from the transistors which will be manufactured?
Okay, so for the BSync 3, BSync 4, they are standardized. So the question is only which values do you input into these models? So the capacities at the gate and such. The size is okay, but so these values which you have to put into the model, they depend on our test wafer, the one which we presented last year. And there we have structures on it where we can actually measure this stuff. So when you process this wafer till the end, then we have these values, and then we can put this into the SPICE, which should be fairly simple, and then we have the correct values.
Und noch eine Frage an Mikrofon 3, bitte.
One more question.
Ich würde gerne wissen, wie groß ist denn so ein Transistor
What's
und
the size
wie
of such a
langsam?
transistor, and aren't they quite slow then?
Okay,
fangen erstmal an mit 1 Mikron.
so we start with 1 micron.
Das heißt also wie soll ich sagen, die Feature Size oder die Länge vom Kanal
So the length of the channel
zwischen Drain und Source ist 1
between drain and source is 1 micron
2 hoch minus 6.
to the power of 6, minus 6.
Ja. Dazu, wie gesagt, das Ratio, also diese Weite dazu, wäre sozusagen dann 1,5
So the
Mikron.
width is 1.5 micron. So that's the size of the transistor.
Das ist relativ groß.
That's
Wir haben aber
relatively big,
in Hongkong,
but looking at the equipment in Hong Kong,
also das, wie wir uns das angeguckt haben, das Equipment ging runter bis 500 Nanometer.
so that equipment would be possible to downscale to 5 nanometers.
8 Mikron Not auslassen und gleich nach 0,5.
So we can just skip the intermediate sizes and just go down to the smallest one. If we had access to equipment which is even smaller, we might have to experiment a little bit more, create a test wafer,
Ja, aber dann können wir sozusagen auch runterskalieren.
but then we can scale down.
Aber wir sind da noch, muss ich auch zugeben, wir sind noch in einem Bereich,
But I also have to say we are in an area which is optically visible.
250 Nanometern, also die Wellenlänge vom Licht, was man optisch noch sehen kann.
So the wavelength of the light, which you can optically see. So our
Das, was
or
sozusagen jetzt irgendwie so
things you see in the microscope,
irgendwie
the stuff which is in current processes you know, they are optically not visible anymore.
man kann sozusagen wirklich mit einer Kamera,
But
USB-Kamera oder so.
optically visible for us means, okay, you can use your USB camera or something else. You can take a photo of the whole chip, and then you can reverse engineer if there is a manipulation on the stuff or not. So it's like a safety feature.
Hier in dem Fall sozusagen als Sicherheitsfeature, dass man es noch sehen.
So it's actually good that you
Dann
can
gibt
still
es noch
see it in
eine
this
letzte
regards.
Frage aus dem Internet.
A last question from the internet.
Ob ihr mal versucht habt,
Did you
Standards
try
für Transistoren eines
to
kommerziellen Anwendungsfalls zu erzeugen?
create standard cells for a commercial manufacturer? If that works, and what would speak against it?
It would work theoretically, yes. What is not working maybe is non-disclosure agreement. So the producers do not want to give the information, and we would have to sign this non-disclosure disagreement.
Physikalischen Eigenschaften haben und so weiter. Also dieses sogenannte PDK, vielleicht habt ihr mal daraus gehört.
The so-called PDK.
Das steht aber unter dem NDE. Die Zellen, die wir danach generieren,
So the cells we would generate afterwards, they would be automatically under this NDA as well. So you could not publish these things.
Kommerzieller Hersteller könnte am Ende diese Tools, die wir hier schreiben, benutzen.
So a commercial producer could use these tools to generate their own cells.
In die Richtung geht.
So in this direction it's possible.
Aber es ist machbar.
Wenn ich keine weiteren Fragen mehr sehe, dann bitte ich nochmal um eine...
It seems there are no more questions, so a warm applause, and thank you also from our...